So let me remind you what the dot product is. So dot product. So I'll just do an example, I guess. So I have vector x, which is say 1, 2, 3. Vector y, which is negative 1, 0, 1. And if I take x dot y, then I multiply the corresponding coordinates. I multiply first coordinate by first, second by second, third by third, and add them up. So I'm going to get 1 times negative 1 plus 2 times 0 plus 3 times 1. So negative 1 plus 0 plus 3, so answer is 2. For example, if I take x multiplied by x, I'm going to get 1 times 1 plus 2 times 2 plus 3 times 3. So I'm going to get 1 plus 4 plus 9, so it's 14. Same way as I take y times y, I'm going to get negative 1 times negative 1 plus 0 times 0 plus 1 times 1. So I'm going to get 2. So what is dot product? You might have seen it quite a number of times. And now a couple of definitions. So if we have two vectors x and y from Rn, we say x and y are orthogonal. Orthogonal will basically mean perpendicular. If you take the dot product, and at the end we're going to get 0. So we're going to say two vectors are orthogonal. If we multiply them together, we're going to get 0. Example, check if the following vectors are orthogonal. Say 1, 0, minus 2, and 4, 3, 2. So all that they have to do, take the dot product and see if dot product equals to 0. If dot product equals to 0, then they are orthogonal. If dot product is not equal to 0, then they are not. So we take the dot product. So 1 times 4 plus 0 times 3 plus negative 2 times 2. So we get 4 plus 0 minus 4, so we get 0. Yes. So it's easy to check if two vectors are orthogonal. Just find the dot product. The dot product equals to 0 by n. Let's do one more. 1, 1, 1. And negative 1, negative 3. I'm going to give it a minute or two to do the calculations and make a conclusion. I believe the answer is supposed to be no. Okay, so let's provide the calculations. So a dot product is going to be equal to minus 1 plus 3 is going to be equal to 1. It's not going to be equal to 0, so no, not orthogonal. Okay, do the following. One more definition. A base B of linear subspace W is called orthogonal if every two vectors from B are orthogonal. So base is orthogonal if you pick any two base vectors, they're going to be orthogonal. So if that's happening, we're going to call that base orthogonal. So let's look at the base. 1 minus 1, 0. 2, 2 minus 1. And 1, 1, 4. So check if B is orthogonal. So we want to check if B is orthogonal. So basically what we're going to do is we're going to check if every two vectors are going to be orthogonal. So we're basically going to check if the first and second, and first and third, second and third, when they're orthogonal. So we're going to check if first times second equals to 0, first times second, third is equal to 0, and second times third equals to 0. So we're going to check the following three cases. First times second. If that equals to 0, first times third, if that's going to be equal to 0, and the last one is the last pair, which we can do is second and third. So 2 minus 1 times 1, 1, 4 is that equal to 0, right? So we're going to check 3. So I'm going to give you a minute to check if that's all is happening. So if all of those is going to be orthogonal, then we conclude that the whole thing is orthogonal. If at least one is not, then the whole thing is not orthogonal. 2 minus 2 plus 0 equals to 0. That's correct. Second one, 1 minus 1 plus 0 equals to 0. That is also true. And the third one, 2 plus 2 minus 4 equals to 0. That is also true. So we checked all the pairs, all the possible pairs in this case. 1, 2, 1, 3, 2, 3. So our conclusion, yes, B is orthogonal. So we still have the same base. 1 minus 1, 0, 2, 2 minus 1, and 1, 1, 4. We know what's orthogonal, okay? So now what we want to do is, we have vector x, which is given to us as 5 minus 3 and say 1. We want to find coordinates of vector x in that base B. Okay, so let's see how we're going to address it. Let's see how we're going to be using that property that our base is orthogonal. So I'm going to write B as U1, U2, and U3. Okay. So this one is U1, this one is U2, and this one is U3. Kind of easy to write the things. Then we are looking for x in base B, which is going to have coordinates x1, x2, and x3 in base B. So it's going to be x1 times u1 plus x2 times u2 plus x3 times u3. Okay. Now to find x1, we'll do the following. So we take x1 u1 plus x2 u2 plus x3 u3. We're going to multiply it by u1. I'm going to distribute u1. So I'm going to get x1 u1 times u1 plus x2 u2 times u1 plus x3 u2 times u1. Okay. So what we're going to get is u2 times u1, because we're talking about orthogonal base, that's going to be 0. u2 times u1, because we're talking about orthogonal base, is going to be 0. So that's the only piece which is going to be left. So it's going to be equal to x1 times u1 times u1. Okay. And if you look what we started with taking our vector x and multiply it by u1. So that's what our starting position. So vector x times u1 equals to its first coordinate in base B times u1, u1. So from here, we can solve it for x1. x1 is going to be vector x times u1 divided by u1 times u1. And as you can guess from here, we also can get what x2 is going to be equal to. So x2 is going to be x times u2 divided by u2 times u2. And x3 is going to be x times u3 times u3. So if we want to find coordinates of vector x in the orthogonal base, it's easy to do it by these formulas. In general, if we have n of them, we'll write down n of these formulas. In this case, it's 3. So, and that's much easier than solving the corresponding system cleaning equations. So let's find what x1 is, x2, and so on. So x1 equals to vector x times u1 divided by u1 times u1. So vector x is 5 minus 3, 1. u1 is 1 minus 1, 0. 1 minus 1, 0 times 1 minus 1, 0. So in denominator, we're going to get 2, 1 plus 1. On top, we're going to get 5 plus 3 is 8. 8 over 2, so we get 4. x2 in the same fashion is going to be x times u2, u2 times u2, 5 minus 3, 1, 1. So 4 plus 4 plus 1 is 9. 10 minus 6 minus 1 is 3. 10 minus 6 minus 3 is 3. So we're going to get 1/3. So go ahead and calculate what x is supposed to be. Right? 5 minus 3, 1. 1, 1, 4. 1, 1, 4. That's 1, 1, 4. So on the bottom, we're going to get 1 plus 1 plus 16, 18. 5 minus 3 plus 4, 6. So 1/3. From here, we're going to get x. And the base b is going to be equal to 4, 1/3, and 1/3. Okay, so it's easy to find coordinates of vector x in orthogonal ways. So we're not going to be solving corresponding system of linear equations. All what we're going to be doing just solving and setting up dot products. If b, which equals to u1 through un, is orthogonal basis, and if y equals to c1 u1 plus cn un, then c1 equals to y times u1 divided by u1 times u1, c2 equals to y times u2, u2 times u2, and so on. Okay. So that's exactly what we stated for three-dimensional vectors, but it's going to be also true for if you have base consists of n vectors. Next thing we want to do is we'll want to consider the following situation. We have two vectors, vector x and vector y. Then if we're working in R2, or in general, not even R2, because we have two vectors, we can pretend that we are working in R2 because there will be a plane which will have these two vectors, right? X and y. So if you pick two vectors x and y, you can always find a plane which will hold these two vectors. Okay, so we always can pretend we're working in R2. And because of that, we can try to kind of visualize that we also have vector z, which is going to be perpendicular to y. So then what we can do is we can try to write down the vector x as sum of two vectors. Okay. One is parallel to y, which is going to be c1 plus y1, and one which is perpendicular to y, plus part which is perpendicular to y. Okay. So often I'm going to be calling it as parallel part plus perpendicular part. Okay. So that's going to be our orthogonal decomposition. So we're going to break our vector x in two pieces. One is parallel to a given vector, one is perpendicular. Okay. So let's do an example. And then generalize example how we could do. So if we have vector x, which is 4 and 3, and vector y, which is 7 and 5. Okay. We're going to write down x, which is parallel part plus perpendicular part. Now, as we did in the previous case, we're going to use dot product. We started with x. Now we take x dot product with y. We know what x is. It's parallel piece plus perpendicular. We're going to multiply by y. Distribute the multiplication. Perpendicular piece is going to be equal to 0. Perpendicular times y, because we're orthogonal, is going to be equal to 0. Then we're going to write parallel in the form c1 times y1. So c1y times y. So again, x times y is going to be equal to c1y times y. So from here, we're going to conclude that c1 is going to be equal to x times y over y dot y. So you see this formula is similar to one which we obtained in the previous, when we were trying to write down vector in terms of inverse orthogonal vectors. So let's move on. Yes, I need to x times y over y times y. That's what we did a second ago. So let's find x times y, 28 plus 15 over y times y is 49 plus 25. 28 plus 15 is 43. 49 plus 25 is 74. So from here, that's what C1 is. And then we can find what will be y parallel. Y parallel is C1 times y. 43 over 74 times 7 over 5. And as soon as we know what y parallel is, y perpendicular is easy to find because x equals to y parallel plus y perpendicular. So y perpendicular is going to be x minus y parallel. So y perpendicular is going to be x, which is 43, minus y parallel, which is 43 over 74. Okay, so it should be straightforward.